Hi, my name's Dan, and this video is one of the short series of videos I'm doing about creating multiplexers, which are part of digital electronics and are a way of routing signals. Actually, let's rephrase that, a way of choosing signals. So you use a control binary input signal to choose which of several inputs gets routed to an output. Um, And this series is part of a larger set of videos that I'm doing, which are demonstrating the development of a 4-bit CPU from very much from first principles right down to the basic logic gates, and doing that developing. So a roadmap of where I'm going for that is down below in the description. Um, we're kind of approaching, not quite halfway through that process yet. We've got quite a way to go. And multiplexers are part of that. Also, I've been using, it's all simulated, so it's using a piece of software called DigitalWorks. You'll see that in action later on in this video, and a link to that is also in the description down below. It's free software. And so the ultimate aim of this long set of videos is a simulated actual digital CPU that is programmable, which has been built up from scratch using logic gates. Okay, it's quite an ambitious aim. So there we go. So as I was saying, this short series of videos within that context are about multiplexers. And so far, we've developed various configurations of multiplexers. But I want to talk about where to go as we go further down this issue of interconnecting signals and interconnecting components, which is something that we're going to need to do um, if we're creating a CPU. So a multiplexer, as I said, is a way of choosing which input you're going to use. And so thinking theoretically about a fairly simple 4-bit CPU, um, you might have a number of different inputs for each component, and so you want to choose from a set of components. So say, for example, we had 8 components in our CPU. That's about how many I'm going to have. I'm not quite sure of the count off the top of my head. The 4-bit components, because it's a very simple thing. So surely this is going to be relatively simple compared with modern CPUs. Well, it is. But if we're going to do this, going to achieve this interconnectivity using multiplexers, then that means that each one of our components is going to need an 8-way 4-bit multiplexer. So that's, in terms of just thinking about how many input pins that's going to be, we can easily build an 8-way 4-bit multiplexer. We can easily then build that into the components. But we're getting quite a lot of stuff going on here and a lot of wiring, and in fact, it's 256 input pins. We can work that out, but we're getting a lot of components and wires when we're doing this. And in terms of actually doing this in hardware, this starts to become prohibitive. 8 components isn't very many, but the increase comes as the more you have, obviously the greater number of inputs each multiplexer has to have for this to connect it. So it rises as a square of the number of components you've got, and then that's multiplied the complexity of how many bits you've got going on as well. So lots of components, lots of wires, and there needs to be some kind of compromise on this. So there is another way of doing interconnectivity. Multiplexers are useful, and we will use them in the long scheme of things in the CPU that I'm creating. But I'm going to flick back to DigitalWorks, which is the digital simulation software, to show this is just it's a diagrammatical thing. It doesn't actually do anything active. It's just to show kind of the principle, which is instead of doing massive interconnectivity, um, uh, you always, in these situations, use a thing called a bus. Um, so it's called a bus because it comes from the concept of a bus in real life, where lots of people can get on and lots of people can get off. Actually, on this bus, you can only technically have one thing on at once. And a bus is basically a set of wires, which is however many bits wide we want. We've got a 4-bit situation, so we're going to be wanting to transfer 4-bit numbers. We might have, as I said, 8 components in our CPU, and we might want to connect from any one of them to any one of them, and that's a lot of different connections, as is fairly obvious. Um, and what a bus does is it reduces the complexity of this communication considerably, but the cost of it is a speed cost, which is that you can only do one transfer of information at any one time between one component which will go out and one component which will read in. So I've created a template here for a dummy bus enabled component or bus ready component. I've created a bus which is the wires, the 4 wires, and I've wired up the 3 of these components. There's no need for me to actually put 8 of them together because that's just a repetition of the same thing. You can see what I'm doing with the 3 here, and each of these components has a set of pins which are the bus pins. And bus, uh, by its very nature, a bus can be used for either inputs or outputs. So there are some wrinkles that go along with this, and we'll explore this further as we get further into the series uh, um, of videos. Particularly the next series of videos is about registers, which are basically memory slots that can read and write from the bus. Um, and I've also got on these bus components 2 other pins, and these pins are labeled output enable and bus read. So you'd need control signals going into these pins to say which component is currently accessing the bus in terms of telling it what the values are. So that's output enable, and you can only have one of your bus components enabled to be telling the bus what the values are at any one time. Otherwise, you have a thing called bus contention, and all sorts of problems can happen as a result. Um, and any number of components can be reading from the bus at any point in time. So taking the bus as an input, and again, so the second control uh, pin here is bus read, which is to if you sent a high signal to that, it would tell this component that you wanted to read the value from the bus into the component. Um, and the components might do all sorts of different things. We've not explored what the different parts of a CPU are yet. Memory is an important part of this. There's going to be some calculation. There's going to be some control. There's going to be some stuff that controls what happens as a result of different instructions, and all sorts of other things going on as well inside the CPU, and lots of different things are going to need access to this bus. But hopefully, as you can see, it reduces the complexity of the number of wires. It means your components can be closer together, which is a quite an important physical aspect in CPU design, because shorter wires means less resistance, which means it's hotter. Sorry, not hotter, less hot, and excuse me, and things can run faster. And speed is often about proximity and how close you can get components to each other inside your overall CPU design. So I haven't actually created anything in this video, just explained this alternate strategy to routing signals, which is to use one wire for each of the numbers in our binary numbers that we're going to use. Everything is going to use the same size of binary numbers. Uh, yeah, that's pretty much right. And then everything's going to talk using this bus. And as I said earlier, the compromise that you're taking when you use a bus is things become slower, but they become less complex. There's a little bit of added complexity in terms of the components and trying to work out this output enable and how to use the bus for input and output, but it's not very big at all, to be honest. And actually, the even though I said the compromise is speed, because of the physical proximity, and in terms of the simulation that we've got here, though, using the simulator without a bus would probably grind the simulator to a halt. And in fact, it means you can run things faster. You end up with a faster clock speed, and things do actually go faster when you use buses than if you use multiplexers all over the place. So you need to pick and choose which strategy you're using for the different parts of your CPU. Anyway, that's a load of talking from me, a little bit of pictures, a little bit of something to look at, and that I think is probably the end of this shorter series of videos, which is about multiplexing and routing stuff. The next series, if you're following on in sequence, is going to be about creating things called registers, which are bus-enabled uh, memory stores. But that's it from me for now.